Okay, let's define the abstract semantic function. That is structurally the same as the one for partitioning abstraction, right? But here we abstract the set of initial states with the composed abstraction function by alpha 1 and alpha 2. Okay, and then we use the abstract step function step sharp. Okay, otherwise the structure is the same. The step function is defined as follows, okay, similar to the one for partitioning abstraction, right? And then finally, the soundness of this analysis is denoted like this, okay? The concretization of this analysis result subsumes the concrete semantics, okay? Then again, let's take a look at the details of the definition of step function. First, the step function and the abstract partitioning function pi looks similar to the ones for the partitioning abstraction. Okay, let's see what does that mean by following these lines one by one. So first, this X, okay, is partitioned abstraction of memories at a certain point, okay, with this type, right? Because it is a function with this type, okay, it can be represented as a subset of this type as we discussed, right? So this is just type conversion. And then let's compute the set of abstract states after abstract transition. Okay, this expression represents that part. Okay, what is the result? The result will have this type, right? The set of abstract states. Okay, and then by regarding these abstract transitions as a function of this type, right, we can rewrite this set as this set. Okay, understand? And then using the previous notation, we can simplify this expression like this, and we can further simplify the expression. Okay, now we are here. And then what is the next? Next, we want to partition the set of abstract states and make a set of abstract memories per label, right? So we transform this set to this map. Okay, this expression describes that part. Okay, and the next, actually, that is actually the definition of the partitioning function pi. Okay, using the expression, okay, we can simplify this expression to this using the definition of this partitioning function. Okay, then after partitioning, what do we want to do? Okay, we will have multiple abstract memories for each label, right? But we ultimately want to merge them by join and make a single abstract state per label. Okay, so this expression represents this one. So we join multiple abstract memories, okay, for each label. Okay, then finally we can simplify this expression using the notation we discussed. So finally we have this notation, this expression. Okay, again, it looks a bit complicated at first, but there's nothing special here. So I strongly recommend you rewrite each line by yourself and understand this definition. Okay, next, let's prove the soundness. Okay, because the partitioning abstraction is a sound abstraction of the concrete semantics, right? It is enough to prove that the memory abstraction is a sound abstraction of the partitioning abstraction. Okay, Then, according to the abstract interpretation framework, the final abstraction is a sound abstraction of the concrete semantics. Okay. And also it can be done by showing this condition, right? This condition is true according to the framework. Okay. Here are the definitions of the two abstract semantic function, f#1 and f#. Okay. So according to the theorem we proved before, right? When we have a complicated abstract semantic function, it is enough to show each abstract operator is a sound version of the concrete counterpart. So in this case, it is enough to show that these two abstract operators are sound abstraction of these two operators from the partitioning abstraction. Okay. Next, let's see the first case. Okay, the soundness of the step sharp function. Okay, which is denoted like this. The proof is simply done as follows. Okay, let's take a look at this one by one. Here, first we expand the definition of step sharp 1 here. Okay, and then next, if we regard this part, right, which is originally a subset of PL times M, which is originally a subset of this set. Okay, if we regard this one as a function of this one, okay, using the notation we have discussed before, then the partitioning function actually redundant, because as I mentioned earlier, if we use the conventional flow sensitive partitioning abstraction, right, the partitioning function pi 1 actually does not play an important role here. And then next, here we assume that this condition hold. Okay, as you can see, this condition means the soundness of abstract transition relation. Okay, we will prove this later. And here we regard this gamma 2, okay, this gamma 2 function, which originally has this type. The input is this type and the output is M, this type. Okay, if we regard the gamma 2 function, which originally has this type, as a function of this type, PM, the output type is the same, but let's take a look at the input type. Okay, because a function, this function can be viewed as a special case of a set of pairs, right? So we can regard this the input of gamma 2 as a subset of this set. Okay, then we can say that this one is larger than this one. Okay, this condition hold. And next, if we partition, right, if we partition this set, using this pi function, okay, and then compute element-wise least upper bound, this one. Okay, then what happens? Because the least upper bound is larger than each argument, right? And then the gamma function here is monotone, right? Then the whole abstract element, this one, is larger than this one. Okay, larger than before, because here the least upper bound, the concretization of least upper bound is always larger than the concretization of each argument, right? Okay, then finally we have this one. That is the definition of step sharp function and comma 2. Okay, so finally this represent the step sharp function is sound. Okay, but there's one remaining thing, right? It is sound if this new subgoal is true. Okay, so let's show the soundness of abstract transition. Okay, here is the proof sketch. It can be done by case analysis. Okay, we have to show that each abstract transition for each command is a sound abstraction of the concrete one, right? Also, it requires the soundness proof for other abstract operators like update, filter, eval, right? Okay, here is the proof sketch. So I will leave this as a practice for you. So the last part of this proof is the soundness of abstract join. Okay, here is the whole soundness proof. As you can see, this one is much simpler than before, so a lot of rewriting here, and we use the monotonicity of gamma function, okay, which is simple. So far we have designed concrete and abstract semantic domains and semantic functions, okay. So this is enough if the abstract domain has finite height, right? But we are now using the interval domain which has infinite height. So we need to define widening operator for termination and narrowing for refinement. Okay. The widening and narrowing for function domains like D# and M# can be defined as pointwise lifting. Okay. Then what does that mean? The essence is actually the widening and narrowing operators for the interval domain. Okay. Once we define the widening and narrowing for the interval domain, and then the widening and narrowing for the other domains like D# and M# can be defined as label-wise and variable-wise lifting of the existing one. Okay. Then let's define a simple widening operator for the interval domain. The first two cases are obvious, so let's take a look at the last case. Okay. This simple widening operator behave like this. Okay. It first checks whether the upper bound is increasing or not. Okay. And if the upper bound is increasing now, then it directly uses the plus infinity as a new upper bound. Okay. Otherwise, it uses the old one as upper bound. The same principle is applied for the lower bound. Okay. If the lower bound is decreasing, right? If C is less than A, strictly decreasing, then it uses the minus infinity as a new lower bound. Otherwise, we use the existing one. Okay. Okay, then let's simply check this widening operator satisfies the widening safety condition. Okay, first, as you can see, the result of this widening operator is always larger than the join of two operands, right? Because if the upper bound is increasing, we directly use the infinity, and the lower bound is decreasing, we directly use the minus infinity here, okay, which is definitely larger than the join of two operand. And then next, this chain by this widening is always finite, as you can see, right? Once the upper bound and lower bound becomes plus or minus infinity, which can be done within finite time, there's no change afterward, right? So these safety conditions hold. The next is a simple narrowing operator for the interval domain. Okay, again, let's take a look at the last case. This narrowing operator, the point is that only takes care of decreasing step with a big jump from infinity to a finite number. Otherwise, it ignores. Okay, what does that mean? So it first check the previous, the old upper bound is infinity or not. If the old upper bound is infinity, then we use the new upper bound. Okay. Otherwise, we use the old one. Okay. The same principle is applied here for the lower bound. We only take care of a big jump from minus infinity to a finite number. So if the old lower bound is minus infinity, then we use this new lower bound. Otherwise, we use the minus infinity as a lower bound. Okay. And then let's check the safety conditions for narrowing. So as you can see, the narrowing result, okay, is always in between two operand, right? And the decreasing chain by narrowing is always finite because it only takes care of a big jump from infinity to finite number, and they don't care the jump between finite number to another finite number. Okay, so the narrowing chain is always finite. So the narrowing operator is also safe.